Hello everybody, I hope you're all doing well. So we're going to continue with general acceleration analysis. Previously we had looked at the idea of general velocity analysis, and I'm going to very quickly recap some of the results that we had from the previous time. But first of all, here are the things that we have so far. Okay, so I have this rigid body which is in the form of this potato arbitrary shape that you're seeing here. Okay, and there is a stationary observer at the point O. Okay, and there is another point B which is a point outside the rigid body. This point B could be a point on some other rigid body. Okay, so this rigid body is the one that is of concern to us. Okay, this is of concern to us because this is the body whose angular velocity and angular acceleration are given, and these are assumed, at least in this particular situation, to be in a direction that is in the E3 direction. Okay, so we're going to assume, so let me make that statement here. Okay, so assume that the vector omega is some magnitude times in the E3 direction, and then I'm going to assume alpha to be likewise as well. Okay, some magnitude times the E3 direction, and E3 is the direction that is out of the plane of the paper. Okay, E3 is a unit vector out of the plane of the page. Okay, so with that said, what we decided to do was we decided to construct a triad of unit vectors. This is the triad E1, E2, E3, as you can see here, right? And this triad is a part of the rigid body, which means that if the rigid body is rotating at a rate omega, the triad E1, E2, and E3 will also rotate at the same rate. Okay, so that's also something that we have seen in velocity analysis. Let me write that as well. Okay, the triad. Okay, a triad of rotating vectors. So you typically write the triad as E1, E2, and then E3, and then you put the clockwise arrows as you show here. Okay, so this triad, the meaning of this is that E1 cross E2 is equal to E3, E2 cross E3 is equal to E1, and then I have E3 cross E1 is equal to E2. Okay, so this is a set of three mutually perpendicular or orthogonal unit vectors. Okay, so this is the triad, and we are told that the triad is a part of the rigid body, which means that this triad, the rate of rotation of this triad is the same as the rate of rotation of the body. Okay, which I hope should be obvious to all of us. Okay, and these are summarized here. So we already mentioned that the point B is outside the rigid body, point A is within the rigid body. Okay, point B is a point either as a part of another rigid body, or it could just be some other particle, which could be outside the rigid body. Omega and alpha are the angular velocity and angular acceleration of the rigid body of interest, which we have mentioned is this potato shaped body with the dark lines, not the dotted lines. Then I have point O, which is the inertial observer who's sitting there. And furthermore, we have also taken this position vector RB/A, and we have written it in terms of the unit vectors E1 and E2 as shown. Okay, and we are looking at planar motion, so that is something that is very important. Since we are looking at planar motion, this position vector RB/A, which is a position of B as seen by A, is not going to have a component in the E3 direction. If it were a 3D problem, then of course, yes, it will have a component in the E3 direction as well. But here it is only in the E1 and the E2 direction. Okay, so things that we have done so far. Okay, things that we have done so far. So far, we have the following. The first thing is we wrote down the position vectors. Okay, so RB is RA plus RB slash A, right? And just very quickly look at this. RB slash O is typically written as RB because we say that if it's an inertial observer, we will lose the subscript O. Okay, so likewise RA slash O, I can write it as RA. If it's an inertial observer, I will lose the subscript O. But it is understood that if I don't have a subscript, then it means that it's an absolute position. Okay, so here RB and RA. Okay, so RB and RA are absolute position vectors. Okay, and then RB slash A is the position of B relative to A. Okay, so this is something that we had seen earlier. Okay, and then I'm going to go to the next thing that we had looked at. We said that, okay, velocity of B is going to be, we had derived this in the general velocity analysis, it's velocity of A plus velocity of B slash A relative plus omega cross R B slash A. Okay, once again here VB and VA are absolute velocity of B and A. Okay, when we say absolute, it means it is with respect to an inertial observer, and then VB slash A relative. And maybe I'll just make a very quick point here. RB slash A can be written as R1, E1, R2, E2. Okay, that's also something that we had seen, and these are what these terms mean. Okay, and then VB slash A relative is going to be R1 dot E1, R2 dot E2. Okay, this is essentially the velocity of B relative to A, keeping the rotation of the body fixed. Okay, so this is the velocity of B relative to A, keeping rotation of the body fixed. Okay, this is one thing, and then omega cross RB slash A. Okay, this is the velocity of B relative to A, keeping the distance between B and A fixed, and allowing the body to rotate. Okay, and in many books you will see that the combination of the last two terms is called as a relative velocity of B with respect to A. Okay, so in many books you will see that VB slash A is equal to VB slash A relative, and then omega cross R B slash A, which essentially tells us that velocity of B is velocity of A plus velocity of B slash A. Okay, this is of the same form that we wrote the position vector in. So another way of remembering it. Okay, so it's the same thing. It's not any different from what we have written so far. Okay, and one more thing, one very last thing that we also came up with. I think let me call that a C. So for a triad E1, E2, E3 rotating at a rate omega. Okay, we know we derived that dE1 by dt is equal to omega cross E1, and then dE2 by dt was omega cross E2, and dE3 by dt was omega cross E3. Okay, so we derived all of these terms for any rotating triad. Alright, now we will come to acceleration analysis. Okay, so now we move on. Go to acceleration. And fairly straightforward once again. I mean, there is nothing much to it. I'm just taking velocity and then differentiating that with respect to time. Okay, so differentiate the velocity equation. Okay, what is the velocity equation? It was VB is equal to VA plus, I'm going to write the full form of this. So this is going to be R1 dot E1, R2 dot E2, and then I'm going to have omega cross RB slash A. Okay, and RB slash A was R1 E1. Let me write my arrows properly on E1. So R1 E1 and then R2 E2. Okay, so this was the velocity expression, and typically these are, if you look at the triad, this is called as E1 dot, this is E2 dot, this is E3 dot, and for us E3 dot is essentially 0. We are not worried about it, but this is in general. Okay, so this is in general. This is in general for any omega. So this holds true for three-dimensional motion as well. Okay, all right, so I'm going to go to the velocity expression, differentiate that with respect to time. Okay, so which means that I'm going to get dVb by dt is equal to dVa by dt plus d by dt of r1 dot e1 r2 dot e2 plus d by dt of omega cross r1 e1 r2 e2. Okay, and then I'm going to just start differentiating this term by term. There is nothing much to it, as you will see. dVb by dt is going to be acceleration of b, then this is going to be acceleration of a, the absolute acceleration of a, and then from here on I start all the differentiation. So look at this very carefully. Okay, first thing is I'm going to differentiate the r1 dot and the r2 dot terms. Okay, so this is going to be r1 double dot e1, r2 double dot e2. Then I'm going to differentiate the e1 and the e2 terms, keeping the r1 dot fixed and r2 dot fixed. So this is e1 dot r2 dot e2 dot. Okay, and then I'm going to start differentiating the third set of terms. Okay, so I'm going to have differentiation of omega, so that's going to be omega dot cross r1 e1 r2 e2. Then I'm going to keep the omega fixed and I'm going to differentiate the r1 and the r2. Okay, plus omega cross r1 dot e1 r2 dot e2 plus I'm going to give the omega fixed, the r1 and the r2 fixed, and then I'm going to differentiate the e1 and the e2. Okay, so then this is going to be omega cross r1 e1 dot r2 e2 dot. Okay, so these are all the set of terms that we have so far. Okay, and then I also want to recall some relationships. Okay, so recall from velocity analysis. Okay, let me underline this particular term here, and recall from velocity analysis that r1 dot e1 R2 dot E2 is equal to V B slash A relative. Okay, so that's one thing. Then the other thing I can also recall is that R1 E1 dot R2 E2 dot, we had obtained this as actually omega cross R B slash A. Okay, so we had actually obtained this as omega cross R B slash A. Okay, these are the two things that we had obtained from the velocity analysis in our previous concept talk. So I'm just going to start substituting for this, and I'm also going to call, okay, so new term or name, okay, R1 double dot E1, R2 double dot E2. I'm going to define it, okay, as equivalent to acceleration of B slash A relative. Okay, it's probably, you can make the relation, you can make the connection, right? Because R1 dot E1 plus R2 dot E2 is VB slash A relative. So R1 double dot E1 plus R2 double dot E2 is AB slash A relative. Okay, it makes sense. Okay, so that's a new term or a new name that we're going to define. So this is not a new term, I guess. A new, maybe a definition is a better thing. New definition. Okay, I guess my colors are a little offset, but I think that's a good thing. All right, so then I go on and then I start doing the substitutions. Okay, so I can substitute for this particular term here. Okay, so I'm going to call that as acceleration of B slash A relative. Okay, then I have one more term that I can do a substitution here. This is going to be V B slash A relative. Then I have this entire term here, which I can substitute as omega cross R B slash A. Okay, then I have a couple of other things to take care of. That's about it. One more thing that you will also recall is that maybe something that I can also write here is that R B slash A, this is equal to R1 E1 R2 E2. Okay, so that's something that you would also recall. So which means that if you look at this term here, that is nothing but R B slash A. Okay, so I have those substitutions performed, so I'm going to clean it up and then write it in the following manner. Okay, so now I have acceleration of B is equal to acceleration of A plus acceleration of B slash A relative. So that's one thing there. Then I'm going to have the next one, which is R1 dot E1 dot and R2 dot E2 dot. Look at this. R1 dot, instead of E1 dot, I'm going to substitute omega cross E1 R2 dot omega cross E2. Okay, that's a substitution that I'm going to perform because I know that E1 dot and E2 dot can be written that way. Then I have omega cross R B slash A, omega dot cross R B slash A plus omega dot cross R B slash A. Okay, that's one thing. Then I have omega cross V B slash A relative, as you can see. Omega cross V B slash A relative, right? These terms are looking a little more scarier than before. Then I'm going to have omega cross RB slash A. Okay, and then I'm going to have omega cross R B slash A. And I just want to make sure that we have taken care of all the terms that we have. Right. Then what I'm going to see is the following. Okay, R1 dot omega cross E1 R2 dot omega cross E2. I can write it in the following form. So this is going to be omega cross R1 E1 omega cross R2 e2, right, r1 dot e1, I'm sorry, and omega cross r2 dot e2, or this is going to be omega cross r1 dot e1, r2 dot e2. But what do you know? R1 dot e1, r2 dot e2 is nothing but vb slash a relative. Okay, so what do I get? I get that r1 dot times omega cross e1, r2 dot omega cross e2 is simplified into omega cross v b slash a relative. Okay, so that entire term has now been simplified into a slightly less intimidating one. Okay, so this entire term is nothing but omega cross v b slash a relative. And what do you know? I already have one more of those things, right? So I have one of those things here as well, which means I can combine them together. Omega dot, I can write it as alpha. Okay, so this I'm going to call as b, and omega dot I can call it as alpha because that is the angular acceleration. And I'm going to now rewrite this entire thing in the following nicer manner. Okay, so now I'm going to have acceleration of b is acceleration of a. I'm just going to write it in the order that is typically written. So alpha rb slash a, apologies, plus this is omega cross r b slash a. Okay, so that is that term that comes from here. This term has a special name. This is called as a vector triple product. Okay, so this is a vector triple product. Okay, this is of the form a cross c. Okay, that's of the general form of that nature. Okay, then I'm going to have a couple more terms, plus a b slash a relative. Then I'm going to collect a couple of other terms which combine together. This omega cross vb slash a relative, omega cross vb slash a relative, if I combine them together, then they're all just going to become 2 omega cross vb slash a relative, and that's about it, right? So that's going to be 2 omega cross vb slash a relative. Okay, so this is the entire acceleration expression, and we're going to look at each of these terms. Okay, so we want to see what these terms actually mean, and to understand that, let's do the following. So first of all, one can simplify some of these things. Okay, so use omega is equal to omega e3, and then r b slash a is equal to r1 e1, and then r2 e2, and can simplify. Okay, this omega cross r b slash a can be simplified into minus omega square r b slash a. Notice that this omega square is a scalar here. Okay, so notice that this term is a scalar, and this is the vector term here. Okay, this r b slash a is the vector, so which means that I still get a vector, which is why it's called as a vector triple product. After performing this triple product, I need to end up getting a vector quantity. Okay, so with this simplification that I am performing here, okay, and this is something that you can perform by just substituting. I'm not going to go through the details of this. Okay, I end up getting the nice form of the acceleration expression. I'm going to list down all of these things. So I end up getting, so finally, final form, okay, of the acceleration expression is the following. Okay, so this is probably the scariest of the three equations that we have done so far, because it contains so many terms that are very unfamiliar to us. Okay, that is the only reason. But once you get to know them well, they become your good friends, and you live a long life together. Okay, hopefully. So acceleration of b is acceleration of a Then I'm going to have alpha cross r b slash a. Then I have minus omega square r b slash a. That vector triple product term becomes this. Then I'm going to have acceleration of b slash a relative, and then 2 times omega v b slash a. Let me make some space. V b slash a relative. Okay, so this is the big guy here. Okay, what is the meaning of all of these terms? Okay, now you will see that to understand the meaning, let me do the following. Okay, so let us say to understand the directions of these terms. Okay, so to understand these terms, okay, so at some point in time, so say at some point in time, r b slash a is coincident with the E2 direction. Okay, just say it. Okay, so at some point in time, it is quite possible, right? This r b slash a could be in the E2 direction at that instant in time. So at that instant in time, r b slash a is along E2 direction. Okay, so let me draw it this way. So I have this rigid body that is sitting here, okay, and then I have the triad of vectors, which is going to be the following, right? So that's going to be E1, E2, and then E3, and I'm assuming the following form, making sure that these are all coming out of the page. So there is one thing that is coming out of the page here, that is the E3 direction. Okay, so this is the E3 direction. Most times it never lets me snap onto these things properly, and then I have to kind of make a mess there. Okay, so this is going to be my E1 direction, this is E2 direction, this is E3 direction, this is the point A on that body. Okay, and then I'm saying that the point B is coincident with the E2 direction, so the point B is probably sitting somewhere here. And so if I draw the position vector, okay, that's going to be along this line here. So let me make sure that it is indeed along that particular line. Okay, so that's coincident to the E2 direction. So let me maybe move that guy there. Okay, fantastic. So you can immediately see that this is the position vector rb slash a. rb slash a is some magnitude in the E2 direction. So let me just call it as R2 E2, okay, because that is the magnitude of this at that point in time. Okay, so this is at some instant in time. That's very important. At some time instant t. Okay, then let me also assume the following. Let me say that, okay, omega is in this direction, so this is omega, which is omega times E3, and then I'm also assuming that alpha is alpha E3. Okay, then I start looking at each and every one of those terms. Okay, so I look at the acceleration expression. So acceleration of b, let me maybe start writing out each of these terms. So first, let us look at the term alpha cross r b slash a. What is the direction of this going to be? So this is alpha E3 cross rb slash a is r2 E2. So look at the magnitude. So this is alpha r2 times E3 cross E2. Now what is E3 cross E2? You got to write the triad. Okay, so every time you do any of these things, E1, E2, E3. Okay, So you got to write the triad, and if I look at E3 cross E2, I'm actually going against the grain, so this is going to be minus E1. Okay, so this is actually minus alpha R2 E1, so which means that alpha cross RB slash A is in the negative E1 direction. Okay, which essentially means that alpha cross R B slash A is perpendicular to R B slash A. Okay, and how to think of it is in the following manner. Okay, it's as if I'm looking at the motion of point B relative to point A, and if I draw a path, okay, so if I maybe draw a path here, so this is a circular path that I'm drawing, okay, and I guess, not sure why that did not come out as a circular path, that is better. Then let me also draw the same thing here. Not necessary, but I could still draw it here. Okay, so this is the circular path. Okay, dotted lines and dotted lines, and then what I'm trying to say is that at that instant in time, this alpha cross RB slash A is actually perpendicular to the direction of RB slash A, so which means that this is going to be tangent to the path of that particular point, right? This is as if I'm fixing the length of I'm fixing the length RB slash A, and I'm letting the body rotate, right? And this is the acceleration that comes out from that particular rotation. So this is going to be alpha cross R B slash A. Okay, and so this is perpendicular, and it is in the same direction as E1, as you can see. And so from that perspective, this term alpha cross RB slash A is called as the tangential acceleration. Okay, so alpha cross R B slash A. Okay, we're going to define this now. This is the acceleration of B relative to A by fixing the distance between B and A and letting the body rotate. Okay, and as you can see, alpha cross RB slash A is a tangent to the relative motion of B relative to A, and as a result, alpha cross RB slash A is called as the tangential acceleration. Okay, so which means that alpha cross R B slash A is called as the tangential acceleration. Okay, so this is the first of the terms that we are looking at, so we call this as A. Then let us look at the next one. Okay, I'm going to look at this term minus omega square R B slash A. Okay, and I'm going to bring out my triad once again. Okay, so let's take this creature. I guess I need some of these things, not all of them, but probably only some of them. So I'm going to copy that, and then I'm going to bring that down here. Okay, and this is the situation that I have. Okay, omega square R times RB slash A. This is fairly straightforward to see. Okay, what is the direction of omega square? Omega square is a scalar. Okay, so this is essentially going to be minus omega square times R2 in the E2 direction, which means that minus omega square RB slash A points in the negative E2 direction. Okay, which means that this is as if this acceleration component, which I'm going to draw here, so this is now going to be the acceleration component that I'm drawing. So this is minus omega square R B slash A, if you look at these circular paths, it is as if this particle B is trying to be pulled towards the center of rotation, and so this is in a sense called as the centripetal acceleration. Okay, so minus omega square or B slash A is also called as the centripetal acceleration. Right. And what is the meaning of this term? As you will recall, omega square r b slash a is the acceleration where we keep the body, the distance between the points fixed, and then we try to let the body rotate because the body is rotating along, and if because the path of the point B is along a curvilinear path, you're going to have two components of acceleration. One of them was the tangential, the other one is the centripetal. This is obviously what we have seen for particles as well. Okay, so that's one thing. Then I come to the third and the fourth terms. Okay, so then I come to A B slash A relative. Okay, this is R1 double dot E1, R2 double dot E2. So in this situation, I don't have an R1 double dot E1, which means that this is essentially R2 double dot E2. Okay, so I can get rid of this entire term here. Okay, so at that instant in time, right, because of the fact that this body was in that position, okay, the position of point B was in the E2 direction. This is in this following manner. Okay, so this is essentially the acceleration of B relative to A by keeping the rotation fixed and letting the distance between B and A change with time. Okay, and this is also, the direction is also fairly obvious to see here. So let me maybe copy all of this, get rid of some of them. Okay, so I'll copy this and then come down and then draw this out here. And you always want to keep drawing the triad. Okay, so that's very important. I'm going to get rid of this term here. I'm going to get rid of somehow that arrow. That's very nice. Okay, and then all I have to say is, okay, hey, this is the acceleration of B slash A relative. Okay, so that's always going to be along the line joining B and A. Okay, so the direction of A B slash A relative is always along the line joining B and A. Okay, so that's very nice. And then the last one, okay, I come to the big one. 2 omega cross V B slash A relative. First of all, this has a name. This is called as Coriolis acceleration. Okay, named after the French physicist Coriolis. There are two contributors to this particular acceleration. Okay, so there are two contributors. One contribution is due to the change in the direction of V relative. Okay, so this is, let's write it this way. Okay, so omega 2 omega cross V B A relative is equal to omega V B A relative omega, quite obvious, right? I mean, 2 times something is equal to 1 plus 1. Okay, now I'm going to call this as contribution 1, and then this is contribution 2. Okay, contribution 1, I will say, is due to, is the relative acceleration of B with respect to A due to the change in the direction of V relative. b slash a relative. Okay, so this is one thing. And then the other thing is, if I look at 2, okay, then this is going to be, I'm going to copy some of these terms due to change. I just want to keep that, but I can. So this is going to be the relative acceleration of b with respect to a due to the change in the magnitude of the position between b and a, due to change in the magnitude of r b slash a, because the change in magnitude of r b slash a produces vb slash a relative if I keep the rotation of the body fixed, right? So this is a change in the direction, keeping the distance between a and b fixed. So maybe I should write that down as well. So let me add a couple of lines down here. Okay, so this is keeping the distance between b and a fixed. Okay, and then I have here the change in the relative acceleration due to the change in magnitude of r b slash a while keeping the rotation of the body fixed. Okay, and then of course what is the direction of all of this put together? Okay, so 2 omega cross v b slash a relative. Okay, this is going to be 2 omega e3, and then vb slash a relative is going to be along the line joining the twos, right? Because this is going to be r2 dot e2. It's going to be along the line joining b and a. Okay, so which means that vb slash a relative, first of all, is going to be r2 dot e2 is along the line joining b and a. This is something that you can see. Same thing as the acceleration, the relative acceleration. In this case, I have e3 cross e2. Okay, if I go to my triad, and I can rewrite this as 2 omega r2 dot e3 cross e2. And if you go to your triad very quickly here, if you go to your triad, e3 cross e2 is minus e1. Okay, so if I copy this figure here, okay, I'm going to bring this guy once again down. I'm going to copy that and throw that into the mix, and we're almost done. Okay, so if I look at e3 cross e2, that's going to be minus e1. So this is going to be minus 2 omega r2 dot e1, which means this is also going to be tangent to the path because this is going to be in the negative e1 direction. Okay, so this term 2 omega cross vba relative is along negative e1 or perpendicular to or b slash a. And something that you want to keep in mind is these are all taking place at that instant in time. Okay, that did not move very well, but just want to make sure that that is attached here. I'm going to get rid of some of these terms. I don't need that. I don't need that either. But then if I draw the Coriolis acceleration, that's going to be tangent to the path, perpendicular here, and this term is the Coriolis acceleration 2 omega cross vba relative. Okay, and that is the Coriolis acceleration. So that's the name that we give it. And so in summary, we can look at some of these acceleration terms very quickly. Okay, the first term was the tangential acceleration. Okay, alpha cross r b slash a. It's tangential because it is tangential to the path. You can think of the point B as traveling along a curvilinear path relative to point A if you keep the distance between the two fixed. And then I have a tangential acceleration, I have a centripetal acceleration. So alpha cross r b slash a is tangential acceleration. Then omega square r b slash a with a negative sign is centripetal acceleration, pulling you towards the center. Then a b slash a relative. Okay, this is going to be the acceleration of b relative to a, keeping the rotation fixed, which means that this is going to be along the line joining a and b. Then I'm going to have 2 omega cross VB slash A. This is called as Coriolis acceleration. That is an important term to keep in mind. And this has two contributions. One is due to the change in direction of the relative velocity. The other is due to the change in magnitude of the relative position. Okay. And we found out that this is also in a direction tangential to the path. Okay. At some instant in time. And in summary, here is my acceleration equation. So summary. Okay, acceleration of B is acceleration of A, alpha cross R B slash A, omega square times R B slash A B slash A relative, and then 2 omega cross V B slash A relative. Okay, so this is the acceleration expression. Two cases, if A and B are on the same body. If that is the case, then there is no relative velocity or relative acceleration. Then V B slash A relative is equal to 0 because the distance between the two is fixed, right? And then A B slash A relative is also 0, which means that acceleration of B is acceleration of A alpha cross R minus omega square R. But if they are on two different bodies, if A and B are on two different bodies, then the most general expression holds true. Then in that case, these two need not be 0. Okay, so I can copy that and I can come and paste that. These need not be 0. Okay, so they need not be 0. And in that case, I have my entire acceleration expression coming from here. Let me just copy that one more time. Okay, so these are not easy things to understand. It takes a little bit of practice, but with enough practice, I think one should be able to understand all of these things. And this becomes the general acceleration expression, where I have the relative accelerations and the relative velocities as well coming into play due to the change in the distance between the 2 points, since they are now on different bodies. All right. So that's the end of the kinematic analysis in terms of equations and so on. All we have to do now is apply them to different types of problems. All right. Have a really nice day, and I will see you in the next concept talk. Thank you and bye-bye.